The purpose of this video will be to learn how to find the domain and range of a given function. So of course, by domain, I'm talking about the set of all possible inputs. So what ordered pairs x, y can we put into a function z of x and y? And by range, the set of all possible outputs. So what real numbers z can I get back from a function by plugging in my possible x's and y's? So I have a function here that I want to look at. Z is equal to x times y divided by x minus y. Let's start with the domain. So just by looking at the function, I can observe that because I can't divide by 0, I need x minus y not equal to 0. That means I need x not equal to y. And I look at it again and I don't see any other issues. So that tells me that my domain should be the set of all ordered pairs, or all points, as long as x is not equal to y. So I'm going to take all ordered pairs x and y and just throw away the ones where x is equal to y. And if I wanted to write that as a set, it would look like all of the ordered pairs x and y such that x doesn't equal y. And that's my domain. Now I want to find the range. And the range is a bit trickier because I need to know all of the possible z's that I can get back by plugging in all of the possible ordered pairs x, y, where x and y aren't equal. And of course, there are uncountably infinitely many ordered pairs x and y that don't have x and y equal. So I have to be a little creative to kind of narrow this down. So the first thing I notice is that because my function is z equal to x times y over x minus y, if I put one of my variables equal to 1, then my function becomes quite a bit simpler. It becomes x over x minus 1. Or similarly, I could have put x equal to 1 and still simplify my function in the same way. So this is just a strategy. I say, why don't I see what happens if y is equal to 1? So in my ordered pair x, y, I'm fixing the y. It's always going to be equal to 1. And I'm going to see what possible z values can I get back when I run over all of the possible x values. All right, so I want to solve this equation, z equals x over x minus 1, for x. So solving it for x, I get z times x minus 1 minus x is equal to 0. So that's zx minus x equal to z. So x times z minus 1 is equal to z, and that gives me x is equal to z over z minus 1. So now I solved it for x. But what did I actually find? So what I found is a form for x that when I plug it back into my function is going to give me any z that I want. So I'll show you what I mean. So in my function, x times y over x minus y, if I let x be equal to z over z minus 1, and y is equal to 1, then x times y is z over z minus 1 times 1. Then I'm going to divide all of that by z over z minus 1 minus 1. So that's x minus y. And simplify. I get on the top still z over z minus 1. And on the bottom, finding the common denominator, I get z minus 1 over z minus 1. And of course, the bottom then simplifies to just 1 over z minus 1. and that's z over 1, which is z. So I can get back any real number z by putting in x equal to z over z minus 1 and y equals 1. But I have to be careful because I already said that x is not equal to y. So what if my x was equal to y? Well, in that case, I would have z equal to z minus 1, just multiplying z minus 1 on both sides. And that can't happen. So that's a good thing. So now I know that z over z minus 1 cannot be equal to 1. So I don't have to worry about my x and y being equal. But now I have one other issue, which is I can see by looking at the denominator of my x value, I have z cannot be equal to 1. So what I'm saying is, I know that for any z, I can get it as an output, any real number z, excuse me, I can get it as an output by plugging in x equal to z over z minus 1 and y equal to 1, except for z minus 1. I'm sorry, except for when z equals 1. So for all z in negative infinity to 1, union 1 to infinity, if I plug in the ordered pair, z over z minus 1, comma 1, then I get the output z. So for any number except for 1, I can say that that's most certainly in my range because the ordered pair that I would plug in is z over z minus 1 and 1. So what about 1? I want to know, can I also find an ordered pair that gives me the output of 1? So let's try setting x equal to 1 instead. And the question that I have in my mind is, can I have z now is equal to y over 1 minus y. That's just going back to my original function, x times y over x minus y, and plugging in x equal to 1. Can I have that equal to 1? So let's explore. Y over 1 minus y equals 1. That means y is equal to 1 minus y. Excuse me, guys. And so I can say then 2y is equal to 1. So y equals 1/2. So I have a solution for if I fix my x equal to 1, then when I put y equals 1/2, I should get 1 as the output. So the ordered pair (1, 1/2) gives us the output z equals 1, which was the only one we were missing. So I conclude that the range of the function is all real numbers. And I've demonstrated how I can get any real number by playing around with these ordered pairs.